Hello, everyone. My name is Tom Adamski. I'm a specialist solution architect focusing on networking. I'm joined today by Akshay Chaudhary, Senior Product Manager at EC2 team. And today we have a tech talk for you on inline and out-of-band traffic inspection on AWS. So if you're building your networking environment on AWS, the VPC would be usually your starting point. And the VPC is your dedicated environment you can allocate IP addresses and deploy your virtual instances into. It's completely private, and you have full control on what that environment can communicate with. Here, in a very simple example, we have a few instances inside our VPC. They all have IP addresses. We have a NAT gateway, and we have a communication path from inside that VPC to the internet. That's a very simple setup, but it can very quickly get a lot more complicated. So our VPC can communicate with other AWS public services like Amazon S3 or Amazon DynamoDB. We can have communication with a lot of different other VPCs through Transit Gateway, through peering, or even using things like Private Link. We can also have connectivity back to on-premise through Direct Connect or VPN. So there's a lot of different components to keep an eye on. So today we're going to try to figure out what's the best way for you to start inspecting what's actually happening on your network. And we split the session into 3 sections. I'll start off with talking about Amazon VPC traffic mirroring. This is our out-of-bound traffic inspection. Then Akshay is going to talk about Amazon VPC Ingress Routing. And then finally, I'll go back to covering how you can centralize inspection from multiple VPCs using the Transit Gateway. So let's start with traffic mirroring. Why did customers ask us for traffic mirroring? So we already had a service called VPC Flow Logs, which would provide you with a lot of metadata information about what's happening inside your network environment. But this wasn't enough. It would give you details on maybe a particular EC2 instance, particular virtual machine is communicating with another machine or the outside world on port 80. But that's pretty much all you'll be able to see. You wouldn't be able to dive inside and understand what exactly is being forwarded. How can you see the actual packet? So with traffic mirroring, customers wanted to have the ability to improve their security and network detection capabilities to actually start seeing the real life packets and then applying filtering and analysis on that traffic. They also asked us to improve the visibility and help with troubleshooting. So with traffic mirroring, you can capture the full packets. You can actually see any traffic spikes in real time there without having to kind of rely on a particular capture window. You can just start seeing the traffic as it's coming into the network. So what are the benefits of Amazon VPC traffic mirroring? First, you no longer need to deploy agents to start capturing information from your instances. So all you need to do is enable traffic mirroring on your ENI on one of your instances and then decide where that traffic needs to be forwarded to. Traffic mirroring also gives you the ability to improve your security posture by looking deeper inside the packets and applying more advanced filtering rules into that traffic flow. And finally, it gives you the wide range of monitoring options. It integrates with a variety of partners and analytic tools that can give you more insight into what's going on into your network. So when we talk about VPC traffic mirroring, we need to look at the 3 components that are building blocks of that service. First component are the targets. So this is where we decide where do we want to forward the captured, the mirrored traffic to. Second component are the filters. So what is the interesting traffic that we actually want to capture? It could be all the traffic, or it could be a specific traffic flow that we're interested in. And finally, the sessions is where we combine all the other components into a working traffic mirroring solution. So let's start with mirroring targets. So today, you can forward the mirrored traffic either to another elastic network interface. So that could be another instance. This is really good for maybe ad hoc monitoring. So you're interested in what's happening on a particular instance, you enable traffic mirroring, you forward it to another instance, another network interface where maybe you're running some open source tools like Wireshark, and you can immediately see what's going on that network. However, a more scalable solution for where you actually start deploying your mirroring on multiple instances, multiple ENIs, you might have a challenge aggregating all the traffic and sending it to a single instance. That's where you would use a network load balancer as a target. Behind that network load balancer, you would typically have a fleet of instances, whether provided by yourself or by a partner, that can help you analyze exactly what's happening with the traffic. Once we have the targets defined, that's where we can start applying filters. And with the filters, you can decide on a particular flow direction, a protocol, source or destination IP addresses, source or destination ports, whether they're single or ranges of ports. And finally, you can decide if you want to truncate your traffic. So maybe you're just interested in the first 40 or 60 bytes of each packet. You don't really need the whole packet end-to-end. So here is a simple example. We have an EC2 instance that's receiving and sending traffic. And we've enabled a traffic mirroring session. That's the symbol next to ENI1. And we now want to start forwarding some of that traffic into the monitoring instance. But in this case, we're only interested in the inbound traffic. And we don't care about anything that the instance is sending. And we can maybe even be more granular. Maybe we're only interested in the inbound traffic that's coming in on port 443 or port 80. And that's exactly the filter we can apply, and that's exactly the traffic that will be forwarded to our monitoring instance. So what's the packet format that you can expect to see in your network when you enable traffic mirroring? So first, there will be an overlay IP header. So this is the IP address of the source and the target that you will see in there. That is then wrapping a UDP header, where we're using UDP port 4789, that then includes a VXLAN header. So you might be familiar with VXLAN as a popular tool for creating overlay networks. In this case, we're purely using this as a way to wrap and encapsulate the captured traffic and then use it as a way to identify it when it's being forwarded to the target. And then finally, inside that VXLAN packet, we have the original packet. So what this also means is that your receiving end, your target, if it's an instance, it needs to be able to parse VXLAN headers and UDP headers, strip them to be able to get to the original IP packet that you're really interested in. This also means that if you're using jumbo frames on the inside your AWS network, and jumbo frames, we support up to 9,001 bytes. You won't be able to capture full jumbo frames because of those additional overheads. So we have to add the VXLAN header, we have to add the UDP header. So the actual maximum size of the packet you can have inside that capture, so the original IP packet, could be up to 8,946 bytes. Okay, so we have a filter, we have a target. The final step is to put it all together. So in this case, we're deciding on which source we want to be capturing. We're deciding where do we want to forward traffic to, and then finally, exactly what traffic are we interested in. And we can actually have multiple sessions on the same source. And each session will have its own priority, and the priority will decide which capture is going to be applied first. So for example, you might have two sessions running on the same source. The first session is capturing only HTTP traffic. And then the second capture is capturing all of the TCP traffic. So the first one will capture HTTP traffic, forward it to the target. And the second session, the one capturing TCP, will capture everything except for the already captured HTTP traffic. So just bear that in mind when you're deciding on how you want to order your sessions if you run multiple sessions on the source. Finally, how do you actually analyze the packets? So let's go back to our familiar example. We have our EC2 instance where it's sending and receiving packets. We then have a monitoring instance. Again, it could be a single instance, or in a more scalable scenario, you would use a network load balancer with multiple monitoring instances behind, and then start forwarding traffic, captured traffic to that monitoring instance. There, you can either build your own traffic analyzer, so using open source tools like Wireshark, or using building your analyzer using Python or Go, or any other language you prefer. You can use open source IDS and IPS tools like Suricata or Zeek, or you can work with large numbers of AWS traffic mirroring partners who can have the software running on those monitoring instances and aggregate the data for you and present it in the format of your choice. So here are some of the partners that we're partnering with. And the list is by no means all exclusive. There's a lot of additional partners that are adding capabilities every day to be able to support traffic mirroring. And with this, I'm going to hand off to Akshay to dive into Amazon VPC Ingress Routing.
Thanks, Tom. Hi, everyone. In the next few slides, I'll talk about what is VPC Ingress Routing, the different use cases of this feature, the biggest benefits of using VPC Ingress Routing, how is it different from VPC traffic mirroring, and lastly, how do we configure Ingress Routing? So what is Amazon VPC Ingress Routing? Simply put, VPC Ingress Routing allows you to associate route tables with Internet Gateway and Virtual Private Gateway. What this does is it provides you complete control over the inbound and outbound traffic. So if you look at the animation to your right, the red traffic packets denote attacks on your workload. Now, suppose if you could attach route tables with your Internet Gateway and Virtual Private Gateway, you could route these packets through a virtual appliance, say a security appliance here. And if this security appliance is able to detect that threat and is able to drop those packets, then your workloads are safe. So to summarize, Amazon VPC Ingress Routing makes it very easy to insert virtual appliances in the forwarding path of inbound and outbound VPC traffic. In the next slide, we look at the different use cases of this feature. So the two main use cases are, the first is that you can route all traffic through an appliance, as we saw in the previous slide. Here, what you do is that irrespective of your workloads, you replace the local route in the gateway route table and pass all the traffic through the appliance's ENI. And a more flexible use case is the second use case. If you look at the animation to your right, what you can do is, suppose you have 3 different workloads and you anticipate different kinds of traffic for those 3 workloads. So you put those workloads in their separate subnets, and based on the destination subnet, you can segment your traffic and pass each segment of the traffic through its own appliance. In doing this, you can have fine-grained security policies for each of your workloads. So if you look at the animation, and at the route table specifically, you see that the network packets that are destined for workload 1 will pass through appliance 1. The network packets that are destined for workload 2 will pass through appliance 2, and so on. In the next slide, we'll look at the biggest benefits of VPC Ingress Routing. There are 3 biggest benefits of VPC Ingress Routing. The first is improved security posture. The second is standardized security across AWS VPC and on-premises network. And the third is you get to pick and choose from a wide range of monitoring options available in AWS Marketplace. So the first, improved security posture. In the previous slide, we saw that by residing your workloads in individual subnet and segmenting the traffic and passing it through its own separate firewall, you can create fine-grained network and security policies tailored for individual workloads. Second, standardized security across networks. Our customers who run their workloads across Amazon VPC as well as in their on-premises network they always wanted to have consistent security policies across both these environments. And many of our customers, they used to route the traffic packets from their Amazon VPC back to their on-premises network, implement those security postures, and then send the traffic back to the Amazon VPC. And this would cause extra overhead as well as latency in their network. But now these customers can run their virtual instances of their on-premises firewalls in the same VPC as the workloads. The third, wide range of monitoring options. So you can select from the many options that are available in AWS Marketplace. And I have a slide showing all our market partners, which is growing every day. And if you want, you can also design your own custom virtual network function and deploy it to fit your need. So we launched this feature last year at reInvent in December 2019 with over 20 partners on AWS Marketplace. And the count is increasing. In the next slide, we'll see how VPC Ingress routing is different from traffic mirroring. The animation to your left shows traffic mirroring, whereas the animation to your right shows VPC Ingress routing. The biggest difference between the two features is that traffic mirroring allows you to do passive monitoring of traffic, whereas Ingress routing allows you to do inline monitoring of the traffic. So if you look at the animation to your left, your traffic will continue to flow to your workload, and then you can enable duplication of your traffic and monitor it parallelly. Whereas in case of Ingress routing, your traffic first passes through the appliance or monitoring device before it hits your workload. So this is the main difference between traffic mirroring and VPC Ingress routing. In the next slide, we'll see how to configure VPC Ingress routing. So the first thing that you need to do is you either need to use your own VNF or select an appliance from AWS Marketplace and set it up on an instance following the instructions. Once you have set it up on an instance, you have to make sure that your workload and your instance, they reside in their own separate subnets. They should not be in the same subnet. Then next, what you do is you attach a route table to your internet gateway or virtual private gateway, and then you add a route that passes through appliances ENI. So if you look at the yellow route in the IGW route table, any ingress traffic that is destined for the workload will first pass through the appliances ENI. The next thing you do is that in your appliance route table, so your appliance resides in a subnet which has its own route table. And in that route table, if you look at the local route, which is in white, that will make sure to pass the traffic that is coming out of your appliance to your workload. Third, your workload sends response packets back to the internet, and you have to add a route which is represented in yellow, which passes through appliances ENI before going to the internet gateway. And once the outbound traffic goes to the appliance, then if you look at appliances route table, you have a yellow route which you need to add to route the traffic that comes out of the appliance and is destined for the internet through the IGW. So this is how you configure Ingress routing. Now, Tom will talk about how to centralize inspection for multiple VPCs using Transit Gateway.
Great, thanks, Akshay. So let's jump into the centralizing of inspection with Transit Gateway. So before we dive into that, let's do a quick recap on what Transit Gateway actually is and what capabilities does it give you. So the best way to think about the Transit Gateway is like a distributed managed router that you deploy into an AWS region that allows you to interconnect thousands of VPCs in that region, allow for any-to-any communication, or you can start limiting that communication if you want as well, and then consolidating that connectivity back to on-premise. So you can connect those thousands of VPCs through the hub and spoke model that Transit Gateway creates back to on-premise using Direct Connect or AWS site-to-site VPN. It also gives you the ability to create different routing domains. So that's where you would be doing more advanced configurations where you can decide which VPCs can talk to which other VPCs and kind of start limiting your communication patterns. So if we do a quick overview here, this is our transit gateway deployed in the region. We now have 3 VPCs in there, but again, we can have thousands of them. And each VPC would be connected to the transit gateway using a VPC attachment. That's a new way for your VPCs to connect to the transit gateway. You might know about some of the other ways for your VPCs to interconnect, like peering or using the virtual private gateway. In this case, we're using VPC attachments attaching to the transit gateway. And again, if we want, we can have those VPCs talk to one another. And then we can start consolidating that connectivity back to on-premise. So let's say we have a corporate data center we want to connect to. We can set up a VPN using the VPN attachment to connect back to on-premise, or we can use dedicated physical connectivity into the AWS backbone, which is Direct Connect, and using things like Direct Connect Gateway to connect to the transit gateway. And then finally, at the end of last year, we've launched the capability for transit gateways in different AWS regions to be able to peer with each other. So if we have a transit gateway in another region with another bunch of VPCs attached to it, we can now create those kind of global networks where VPCs in one region can communicate with VPCs in another through our transit gateways. So transit gateway, very powerful construct. It will also include all of the routing tables. So the transit gateway would have its own routing table that allows you to decide how traffic will be forwarded. So again, by default, you could use a single routing table for all attachments, which would mean that VPC1 can talk to any of the other VPCs. It could also talk to on-premise, and it could talk to the transit gateway in another region. As long as the routes exist on the transit gateway, the traffic will flow. So today, we're going to focus primarily on using the transit gateway for centralizing your egress filtering. So the goal for us is to have multiple VPCs without direct internet connectivity, but when they are trying to communicate with the internet, we want to forward the traffic to the transit gateway and then to a VPC where we have some filtering appliances, firewalls, something that can do that inline inspection and help us see what's going on the side of the traffic. And there's 3 different ways on how you can attach those security appliances to the transit gateway and how you can put them in the path. And we'll explore each one separately, looking at how the routing needs to be set up, as well as how you can set up high availability to make sure that the traffic can still flow if there's any failures to your appliances. So let's start with the VPC attachment model. And we're simplifying the design here a little bit. We have a VPC on the left. This is our source VPC. This is where we have an instance that needs to communicate with the internet. That VPC doesn't have direct internet access itself. Then we have a VPC on the right. This is going to be a security VPC where we will have our appliances. You can see that VPC has an internet gateway, so it's able to communicate with the internet. And we have 2 subnets in there. So when we zoom in into how the transit gateway is actually attached to that VPC, you'll see that transit gateway would have an elastic network interface or an IP address in those 2 different subnets. And those different subnets are in different availability zones, which means we have high availability in this scenario. If there's an issue with one availability zone, we still have traffic flowing from the transit gateway through the other elastic network interface. The important thing to remember here is traffic can arrive of whichever one of those 2 interfaces, so in whichever one of those 2 availability zones. The next thing we need to provision are public subnets, so subnets that will have reachability to the internet through the internet gateway. And that's where we will provision our security appliances, in this case, firewalls 1 and 2. The next thing to configure is routing. So we need to make sure that the VPC routing table has a default route sending all the traffic to the transit gateway. We need to configure a route on the transit gateway to say that any connections to the internet should go to attachment 2, so to security VPC. And we also need to make sure we have a return path to our application VPC on the left. And then when traffic arrives inside the security VPC, we will then have different routing tables associated with the subnets where we have our transit gateway ENIs. And as you can see, depending on which availability zone, which ENI the traffic arrives on, we will be forwarding that traffic to the respectable firewall in the same availability zone. So if the traffic comes out in the ENI at the top, we will forward traffic to the firewall at the top. And then the subnet and the route table associated with the firewall at the top will have a default route pointing through the internet gateway, and the same applies to the firewall at the bottom. Again, both firewalls need to have a path back for return traffic to work. So if we analyze how a packet actually gets forwarded, here we have the instance being the source of the request, and the destination, maybe it's Amazon.com. So it will be resolved to a public IP address. So imagine the source is a private IP address, destination is the public IP address behind Amazon.com. So the default route in the VPC sends it to the transit gateway. The transit gateway then will forward it to one of those two ENIs in the security VPC as per the route in its routing table. If we end up in the ENI at the bottom, we'll apply the route configuration in the routing table at the bottom, which forwards all the traffic to the internet to firewall number 2. At this point, the source is still our instance, the destination is still the public IP address on the internet, but the firewall needs to do source address translation. So we will need to translate the IP address of the source instance to its own public IP address, and then forward the traffic out to the internet through the internet gateway for following the default route. So in this point, we have the instance in that one VPC, or we can have multiple VPCs. All of them would be forwarding traffic to one of those two firewalls and then forwarding it out to the internet. Now let's look at achieving high availability in this scenario. So what if one of those firewalls has a failure? So it's an EC2 instance-based firewall. So if it fails, it will disappear, but the route in the routing table will still be there. So if the firewall goes down, what will happen is that route effectively will be blackholing all our traffic. So with the VPC attachment deployment, we need to make sure that we have some automation, even either developed by yourselves. So as the customers need to create their own automations, or some of the security partners, security vendors will provide recommendations on how to set up the automation in case there's a failure. And it usually means there will be a script that will update the route table at the bottom to point to the firewall at the top if firewall number 2 is down. Okay, so what about a different model? In this case, the VPN Attachment Model. So on the left-hand side, we still have the same setup. We still have our instance in our VPC, still no internet gateway. In our security VPC, we still have our two firewalls in different availability zones, so still they're highly available. But instead of using the native attachment to the VPC, we effectively run AWS site-to-site VPNs from each firewall to the transit gateway. And those VPNs will be running Border Gateway Protocol, which is a routing protocol that allows those firewalls to inject a default route to the transit gateway. So let's see how the routing is going to look like here. So the VPC on the left, still the same default route for the transit gateway. Now, transit gateway will learn the default route from each one of the firewalls. And if you enable ECMP, this is equal cost multipath. It's a protocol that allows you to utilize multiple paths if you're forwarding traffic to the same destination. And in this case, we have two firewalls, so we have two paths where the default route will point, and we will distribute the traffic across those two VPN tunnels. And then once traffic gets to one of the firewalls, again, we'll apply the routing table in the subnet of the firewall to forward the traffic out to the internet gateway. So let's have a look how the packet will flow through that scenario. Again, instance on the left, sending traffic to Amazon.com. That's going to be a destination, a public IP address on the internet, so it's forwarded to the transit gateway. Transit gateway then uses one of those two default routes it learns from the firewalls. Maybe it picks the one on the bottom again, and traffic gets to one of the firewalls. The firewall, again, needs to do source NAT to make sure the traffic always comes back to the firewall that handled the outbound traffic. And it will forward it out to the internet using the route to the internet gateway. So what about high availability in this scenario? So in case one of the firewall fails, that site-to-site VPN tunnel will go down, and the BGP session will also go down, which means the route to the firewall that fails will be automatically removed. So in this case, we have really nice automatic failover, so it's very easy to not have to worry about creating any scripts. However, the downside of setting up firewalls as a VPN attachment is potential impact to the performance. So now our firewalls have to deal with additional encryption, so they may not be able to handle as much traffic as they would with the native attachment. And finally, let's look at the final model we see for egress filtering, and that's forward proxy model. So in this scenario, we still have a VPC on the left, we still have a transit gateway, back to the native attachment to our VPC on the right. But instead of using firewalls that would be routing and NATing, we will set up proxies that will be terminating a TCP connection from the instance and then reinitiating that connection to get to the internet. And to make those proxies highly available, we would typically deploy a network load balancer in front and point to those proxies as a target. So the instance doesn't connect directly to a proxy, but rather connects to the network load balancer that then forwards traffic to the appropriate proxy. So let's have a look at the routing here. So the first big difference is the VPC on the left doesn't need a route to the internet anymore because all of the connections will be going to the proxy IP address range. So then the transit gateway route table also doesn't need a default route because all it needs to know is about all the VPCs that are attached to it, especially the VPC where we have the proxies. The subnet route table, all it will have is a local route. It also doesn't need a default route because the traffic coming in through those attachments will effectively be targeting the network load balancer IP address, which is the 10.2.something IP address. And then finally, the route table of where the proxies are, that's where we would need the default route to be able to get to any destinations outside on the internet. So let's follow a traffic flow. So here we have a packet going from our instance. This is our source. But in this scenario, we had to configure the instance to explicitly use a proxy when sending traffic out to public destinations. So if it's connecting to Amazon.com, the proxy configuration would force it to send a request to the destination being the NLB before it actually gets forwarded to Amazon.com. So we're sending traffic from the instance to the NLB in the 10.2 range. The transit gateway forwards it exactly unchanged. Traffic reaches the network load balancer through the ENIs and then gets forwarded to one of the proxies. And the proxy terminates the connection and then initiates another connection from its own IP address. So we can see here the source is the proxy, and now the destination is the Amazon.com destination, Amazon.com public IP address. And the way the traffic is forwarded to the internet gateway is through that default route in the IGW. What about high availability in this scenario? That's again very simple. If we have a failure of one of the proxies, the network load balancer would actually run health checks to each one of the proxies, and as soon as it realizes that one of the proxies is unavailable, that proxy would be removed from the target pool, therefore not be used for any traffic forwarding. You could also use things like auto-scaling to automatically expand the number of proxies as your amount of traffic grows. And the big benefit of using the proxy model is it's much easier to deal with decrypting traffic. So if you have TLS flows that are typically really hard to decrypt, because you're terminating them on the proxy, you'll be able to inspect even encrypted traffic connecting to the proxies. Okay, so if we summarize all three models side by side, we had the VPC attachment model. That's where we are routing to the firewall appliances through the transit gateway. As you remember, we don't have to do encryption, so there's no performance penalty for that model, but we do have to figure out how we will do failover. How do we automate our route updates if there's a failure of one of the firewalls? Then we have the VPN attachment model, which is kind of automatically handling a failover using BGP. But at the same time, it means we're using encryption, so we're potentially paying a performance penalty for that traffic. And finally, forward proxy model, where we have no encryption in this case. We have high availability provided automatically by the network load balancer. It's much easier to deal with decrypting TLS traffic, but in that scenario, for every single client that will try to connect out to the internet, we have to make sure it has the appropriate proxy configuration on it. Okay, so to summarize, We've covered a lot of different services here, covering how you can do traffic inspection. We talked about VPC traffic mirroring when we were looking at how you can do your inspection out of bounds. So send your traffic off to another appliance that will then do analysis and provide you information of what's happening with the traffic, whether for security purposes or kind of just understanding the traffic flow. Actually, I also talked about Amazon VPC Ingress Routing, where it allows you to do transparent inspection in a single VPC. So you can add your firewalls or inspection appliances as a bump in the wire without having to do any source address translation, so you don't have to do any NATing. And then finally, for those larger environments where you have multiple VPCs and you want to centralize your inspection and filtering for a centralized set of appliances, that's where you could use Transit Gateway. But you remember there's different ways of integrating with the Transit Gateway. And in all of those cases, you actually do have to do nothing. So you will have to do source address translation on your firewalls or appliances. Okay, thank you very much. And with that, I'm going to open it up for questions.